Bond convexity and convexity adjustment. Interest rate risk refers to a bond's price sensitivity to changes in its yield. So the percentage change in a bond's price could be divided into two: duration effect and convexity effect, or we could say convexity adjustment. Duration effect is equal to negative annualized modified duration times the change in YTM. Convexity effect is half times annualized convexity, then times the change in YTM squared. From here, we could deduce that this convexity adjustment formula is obviously nonlinear. It is nonlinear because there is raised to power 2 in this equation, which simply means we are dealing with an equation that looks more quadratic, that is nonlinear, or we could say that the convexity adjustment has a second order effect. So it has a second order effect because of these two. But looking at this duration formula, it would obviously be linear, and we could conclude that it has a first order effect. Modified duration measures the linear effect of changes in YTM on a bond's price. As said earlier, modified duration has a first order effect. However, larger changes in YTM are captured by convexity effects. Convexity becomes important as it accounts for the nonlinear effects on price, or we could say as it accounts for the second order effects on price. So the percentage change in a bond's price is equal to the whole of this. It is worth noting that the whole of this is duration effect, and the whole of this is convexity effect. So that we are all on the same page on this point here about capturing larger changes in YTM, let us look at this example. Let us assume that annualized modified duration is 4 and annualized convexity is 100. Now, let us consider this small change in YTM, that's 0.1%. Inserting this small change in YTM of 0.1% into this formula, so it will be negative annualized modified duration, that's negative times 4, then times the change, that's the change from the increase in yield. Converting that to decimals will be this. So if you solve for the whole of this, the duration effect is this. To compute for the convexity effect, it will be 0.5 times annualized convexity, and that is 100 from this example, then times the change in YTM squared, and you should have this. But it is worth noting that the whole of this is 0.000001, which entirely dilutes the effect of convexity adjustment. If you add the duration effect, if you add it to convexity effect, this is what you will have. That implies that the percentage change in the bond's price is this. So this is very close to what we have here. If you convert this to decimals, it will be very close to what we have here. That implies that the major contributor of this percentage change in the bonds price is duration effect. But if we were dealing with a larger change in YTM, so when dealing with larger changes in YTM, then the effect of convexity would be of great importance, because at that point in time, convexity would contribute a relatively large portion to this percentage change in bond price. So the relationship between price and yield is actually this effect, this curvature shows the relationship between price and yield. So the relationship between a bond's price and its YTM is curved. Convexity helps better approximate the bond price change when YTM change significantly. And that is still referring to these larger yield changes.